Okay, well, thank you for that introduction. And it's a pleasure to be here. Well, not really. I'm sitting in my office where I normally sit, but it would be much nicer if I was able to travel somewhere. But having said that, what I want to do over the next 40 minutes or so is to look at design and artificial intelligence at a particular trajectory of that. The design is one of the foundational activities of humans. It's surprising how ill-informed we are about design compared to lots of other things that are around us, given how design is the way in which we change the world. And then, you know, in the last 50 or 60 years, fraction longer, there's this new intellectual activity called artificial intelligence, and design has always been interested in intellectualizing and also in borrowing and making use of ideas. So it's not surprising that artificial intelligence was looked at and then taken up in various ways in design. So let me just start with a little bit about the past, a little bit about the present, and a little bit about possible futures. So hopefully things happen. Let's just very quickly look at what are the capabilities of AI. And these are things we all know, and there's nothing really special about that for us. AI is full of capabilities. In some sense, it is just the sum of capabilities, but let's proceed. The basic things that people talk about are representation and reasoning. You represent symbolically, you reason symbolically. That's really different to things we've had before. And this moved very quickly to vision. And then sometime later, natural language processing, building symbolic systems to match natural language. And then even later, the notion of sensing the environment. This, of course, takes us to robots. And then the hottest topic 40 years ago is again the hottest topic, which is learning. Without learning, a system is static. It just ends up repeating. And then roughly at the same time as AI started, cognitive science started up. Cognitive science deals with structures of the mind. And not surprisingly, we get to a confluence of AI and cognition. And there's many more. So these are the sort of backbones of AI. And what's missing from this as a designer? Well, designing is about generation, producing things, not about learning from only about learning from the past. So maybe we need to sort of think of AI not in the way in which AI researchers and users think about it, but in perhaps a slightly different way. And then there's something fundamental about designing. Designing is about framing and reframing what it is you're doing. So that makes it truly different. And I'm actually having a lot of problems here. But so let me start off with the sorts of things that I'm just not sure why this isn't. Here we are. So in the late 1960s, when we started teaching computers, we discovered AI, mainly in the form of rule-based systems. And with students, we were able to use rules on graphic elements. And whilst these are not the outputs from 1969, these are redrawn. Because in 1969, We didn't have such high quality output. These were all printer outputs. We were able to discover that with rules, you could generate an amazing array of patterns, and it exhibited something which turns out to be quite important, which artists are familiar with, architects somewhat less so, and that these patterns had emergent properties. What is that? Properties that you didn't put there. And so, for example, on the left, if you take that red shape and just move it up and down and repeat it in a certain way, you get an emergent property, which is the cross, and so on. So this was pretty interesting for the late 60s. But we discovered very quickly that, yes, that was fascinating. You could do all sorts of things, but you couldn't predict anything with it. And so we discovered this, what was then a hot topic called machine learning. And I had a consulting practice for large buildings. And one of the questions always was how big to make the lobby of the elevator shaft. And nobody knew. They said, oh, 1 square meter per person, no, 3 square meters. This clearly doesn't make sense because it depends on the size of the building, how many elevators. So we went around, Alexei Marmot, who was an undergraduate student. We went around and measured 54 office buildings and did some machine learning over them and produced, in this case, an equation that allowed you to predict, based on that corpus of buildings, how big to make the lobby area. And we published this in 1976. Then rule-based systems coalesced into what were then called expert systems. Expert systems used rules, if-then rules, to encode knowledge. And Bala Balachandran, Mike Rosen, and myself built this system, which we got funding for, to take the building code and turn it into an expert system. And we connected that to AutoCAD. And we could now start to semi-automatically check designs against the building code, which was pretty good, particularly for its time. Right? I don't know if you, this was sort of in the 1980s. We had access to what was then very sophisticated machines, Sun Microsystem workstations, and we could run these. And we actually built systems commercially based on things like this. Then, working with Rivka Oxman, we tried to invert that. So we used the knowledge base in the building regulations, but inverted them to allow us to generate designs. Now that's full of interesting issues, which are actually quite hard, but this is an interactive knowledge-based CAD system. This was also in the 80s, 1980s, not 1880s. And Richard Coyne took this notion of generative rules and in a much, much more sophisticated way, built logic systems that allowed you to explore design spaces that could be generated by simple rules. But at that time, learning was pretty minimal in terms of what you could learn. And if you people interested, the basic system then was ID3, which was a statistical entropy-based modeler for learning. And it just didn't seem to match the sorts of ideas that designers have. So I came up with an idea which is modeled on genetic engineering. And Vladimir Kazakov and I built a system that was based on this idea. That is, you take all your designs, they're represented genetically, you divide them into good designs, bad designs, and you look inside the genome of the good designs for structures in there that appear only in the good designs and not in the bad designs, and you learn those structures. What does this look like? So here's learning Frank Lloyd Wright houses. So here's the 3 floors, the 2 floors and the roof of a well-known building. And we could learn a set of genes, which here are expressed in the outlines of the spaces, and the colors represent functions, and use those genes to design, not to design, because to generate buildings of that style that Wright didn't design. So it turned out genetic engineering actually had some nice ideas behind it, even for the evolutionary computation world. So now we're in the sort of mid-90s, and you can do all sorts of things. Here's some original Mondrians, and this is the expression of the Mondrian genes that we've learned. And here's some Mondrians that are generated. They're not very good, but the main problem with them is that they're separating lines aren't right, but a bit more learning, and we actually got them to be quite good. And then came the question, what can you do with it? I mean, it's always interesting to do such things, whether you're generating Wright houses that Wright never designed or Mondrians that Mondrian never painted, but can you do more? And of course, this is the interesting question as designers. Can we do things that make it richer? So here's something you can't do in nature, which is to allow Mondrian and Frank Lloyd Wright to mate. Well, I don't mean the men, I mean their genes. So on the left are some truly unfortunate looking genetically engineered Mondrians. And on the right are some genetically engineered Frank Lloyd Wright windows. Now, if we have some human AI interaction and we force these two to mate, we end up with something we call Flandrians. And here's a Flandrian. This is a Flandrian. This system has a little more in it that has dominant and recessive genes. So on the left is Frank Lloyd Wright's genes are dominant and Mondrian's are recessive. On the right, it's the reverse. Mondrian's genes are dominant and Frank Lloyd Wright's are recessive. The genes are not lost. So now we're able to produce something not only that never existed before, but conceptually never existed before. There was no such thing as Flandrians before we did this. And that's a big claim to make, that we've created a space that just never existed before. So one of the questions always is, where do ideas come from for humans? And where can ideas come from using AI? And this was an interesting topic in AI as well as in design. And the place AI worked on was analogy. That is, drawing ideas from somewhere else. And there was a very well-developed system, the structure mapping engine, developed by Deirdre Gentner, but it sort of produced boring designs. So what we looked at, and this is, this is with Lena Chiang, was to look at designs, ideas from things that were far from what you were designing. So we're just designing doors, and this is a system that looks for things that are semantically unrelated in every sense. That is, there's no terminology that connects the design you're drawing ideas from. So it needs a different way of representing the world. And this is an example. We're designing a door, and it says I can get ideas from taps, and it tells you what the idea is. So it replaces the hinge with a horizontal gear mechanism. And that's pretty neat, very simple. And then we looked at things where it matters what words you use. So we were looking at not just designing bottles, but bottles that are used for traveling and bottles that are personal use. And all three of these words are semantic words. So it has to look around to find things associated with those ideas. And what is even meant by that? So bottles are containers, travel is a space restriction, personal generally means close to you or small. And this is the basic idea it found, that zippers occupy less space when you activate them. So it tried to draw an analogy from zippers, and this is what it comes up with. So here our goal is, this is research work, so we're looking at the underlying processes, but our goal always is to be driven by the notion of designing, and designing is about constructing worlds and generating things inside those worlds. And then this is some really nice work done by Rob Saunders on how you could get an AI to self-learn. No human involved in this, except for the sketch on the left-hand side. The human drew those two overlapping squares, and this is a system that has one thing in it only: look for regularities. That's its motivator. And find anything you can with regularities. It uses ideas from Donald Schoen on reflection in action. It uses notions from situated cognition, and eventually it finds concepts that map onto horizontal lines, to line segments, vertical lines, vertical segments, and slowly down the bottom, it's generating, putting these things together on a screen and then parsing the screen. It slowly learns how to generate sloping lines and so on. And if you let this thing run for a very long time, it comes up with an extraordinary number of geometric concepts. And that's an interesting thing for people. The next step you notice I'm jumping roughly every 10 years, is to add cognition to AI. So AI is concerned with generating systems that exhibit some kind of intelligence. And there's two kinds of AI. There's strong AI, sometimes called good old-fashioned AI, and then there's just AI. One of them is concerned with modeling humans on the basis that that's how you get to intelligence. The other says, let's just produce machine intelligence, intelligence exhibited by machines. Cognitive science doesn't look for that. What cognitive science looks for is it looks at the mind and tries to find ways in which you can structure the mind that allows you to understand the mind. Whoops. Somehow or other, getting into this Zoom has done interesting things. Don't look at this too carefully, but just to show you that what we have here is a fundamental psychology architecture, which is, it takes in things, it builds conceptions, it posits actions, and then it builds this effect on the environment. And to do that, it needs sensation, perception, and conception. These are different kinds of neural networks, all self-organizing. Some of them are unusual. And what it tries to do is to take account not just of what's happening in the mind, but the interaction that an embodied mind has with the world outside it. And that's sort of this notion of situated cognition. And from that, we can build all sorts of things. So, for example, I'm going to show you in a minute objects which we're going to model as cognitive agents. An agent is a computer program that's sort of autonomous. It has these ideas of perceiving, sensing the world, building not necessarily a model of the world, but a perception, and then working out what to do next. And what have we got here? The red are requirements, and the things that run around are components which are going to self-assemble to meet the requirements, and the lines are interactions that are generated as components assemble. So this is what you see as this system is wandering around, meeting requirements and generating requirements as they assemble. Here we are. Of course, the hottest topic today is deep learning. Deep learning's been around for maybe 20 years, but only more recently has it got to the point where the technology has progressed where you can do serious things. So what makes deep learning interesting for designing and, well, for designers and design researchers is not that it learns, but because of the way it learns, it parameterizes everything and produces a very large design space. By very large, I mean very, very, very large. We don't need to go into how deep learning works, But what's interesting about it is this notion that it creates this very large design space that covers areas that would be very hard, if not impossible, for humans to reach. But from a design perspective, there's some things it just doesn't do well. And it really isn't very good beyond the boundaries of the corpus from which it learned. And you think, well, that's okay. The design space is so big that we're not going to miss much. Well, I'm going to suggest that's not the case. In fact, notwithstanding its enormous capability, it's fundamentally flawed. And I will explain why. Not as a technology. As a technology, it's magnificent. And in its use in design, will occupy us for years. But it's got a fundamental flaw. So you can use this to generate designs by learning from previous designs. And this is some work done in designing chassis for a drone. And this is just wandering around the design space, which was generated by looking at a very small number of chassis. And look at the range of designs. And it goes on and on and on. I mean, there are umpteen millions of designs in that design space. But they all share something. They're all connected. What happens if you come up with an idea where it's not connected, like you connect them separately to something? That's not possible here. You cannot have ideas that are not implicitly embedded in the training set. And you can test this with very large databases. The biggest database at the moment is behind a system called GPT-3, which has billions of words in it. And it's a system for generating sentence, word, sentence, paragraph, and story completion. And it's remarkably good if you shepherd it. But if you're in the poetry business and you want to join words together in a novel way, it doesn't like it. One has to recognize the limitations of the technology one uses. But you can do absolutely incredible things with deep learning. Here's the flow of molecules around a cylinder. And you just point a camera at it and pick up the location of these molecules. Run it through a deep neural net, and it will predict what this plume looks like. This is what the theoretical solution looks like. And if you do some symbolic learning over the learned model, you can extract some equations. Navier and Stokes, a couple of hundred years ago, theoretically worked out what these equations were from a very deep understanding of the phenomenon. And if you look at the deep learning learned model, it's so close, yet the deep learning has no understanding of anything. So there's true power in this deep learning. but it's not the solution to everything. So maybe there's new ways for doing learning beyond deep learning. So here's a system where a robot is sorting things. A human is looking at them. There's an EEG cap measuring the electrical signals. And all the human is doing is thinking, oh, they got that one right, got that one wrong. That's it. The robot is learning from the brain signals of the human. And now this is a very simple evaluation task, but humans are really good at evaluating things without knowing how they're doing it. So one could imagine applying this to designs. You generate designs. I can't really explain what is so good about this, but the entity is good. Well, I don't like, there's some aspects of it. So you could imagine new ways in which you can teach AIs. You could imagine new ways of interacting with AIs, which that's not it, is it? It's to turn, assuming we can get AIs as generators, how can we co-create with them? Now, maybe we put new interactions and co-creation together. And here's some work done by Sarah Abdullahi, where the AI generates completions of sketches, and is also looking at the emotional response of the designer to their generations, and responds to the emotion, not to someone saying, I like this, I don't like this. So now we've combined physiological behavior of the designer with the AI generator. Now, we often talk about design spaces, the notion that it's an abstract idea, the world within which the designer works, but it's not necessarily an abstract idea. Here's 19 design teams it's 57 designers. And this is the entire space of ideas they're working with. There are no ideas which they enunciate that aren't here. And the size of the letters on the nodes are how many of these designers talked about these ideas. And in this particular case, we're characterizing the design space. It doesn't matter how, but no, we're able to distinguish, and the blue and the red have meaning. So we can take this other aspect of AI, natural language processing, and now start to get into design spaces. And then we can start to use AI as a facilitator. And this is some very recent work where I wanted to get some funding, and the funding body said, yeah, this looks like neuroscience. We're not interested in neuroscience. We're interested in engineering design. Make it useful for engineering design. And so I came up with this idea, and Trip Sheely and we've now got some funding. What does it do? It's based on the idea that high-performing people have coaches that give them feedback. Now, students get feedback from their tutors, their teachers. Designers develop feedback themselves. But can you improve what humans naturally do? Because you can take an athlete and dramatically improve their performance. So here's the idea. You measure somebody's brain activity, a designer's brain activity. And you can show through a heat map which part of the brain is really active when they're coming up with ideas. And we start off by saying, we show them this, and all we say is, keep that part of this graph red. That's it. We don't say anything else. And this is what happens. On the left is the control group, who aren't told anything. And so this is a frontal view of the brain. It's like you looking in a mirror. And the red is the more red, the more active. The more blue, the less active from the rest state. The neurocognitive feedback group, look how much increased activation there is. You say, well, yeah, they're asked to do more, but there's meant to be something right here, and it's not. They produce twice the number of ideas. This, by the way, is the results. This isn't one person. This is a pilot study with 30 people. So, and now the next step is to learn all this as an AI. So you don't need to do this. You can retrain people, or people can retrain themselves. You can retrain your brain, which you're doing all the time. So now we've gone from, here's this disembodied AI, to connecting AI to ourselves. Now, I want to finish off, we started a bit late, but with the notion of the AI singularity, which people talk about. When AIs are as capable as humans and have the potential to take over from humans. And of course, there's a parallel AI in design singularity. So here's some fundamental questions to this notion. AI is basically a set of capabilities. Is human activity a sum of capabilities, or is there something more? Well, this may be a philosophical question, but it's almost a physical question as well. The other thing is that the world is truly messy. You never get everything. And here's a robot that's told to put that box on top of that tray, that trolley. Let's start from the beginning. Pushes that thing off, it hits something, pushes it away, it thinks it's in the right place, drops its arm, the arm catches. It wasn't told about any of this. It was told, find the object you're going to drop your box on. When you get there, drop your box. Everything else is unintended. What a mess. And then, of course, there's questions of ethics. The minute you embody things, and it applies to design, perhaps even more than anything else, embodiment reifies one's ethics, whether you intend it or not. So here's some basic questions for AI as a design singularity. Is it the sum of capabilities? And what makes designing different to other tasks? It's generative. It creates the space within which it's going to work. It's not given that space. I mean, some people use the same space as everybody else. The goals aren't all fixed. You change the goals as you go along. That's not a good thing if you've got a consulting project with a problem to solve with a fixed goal. People don't like it if you say, well, I've solved somebody else's problem. In designing, you can deal with lots of issues. And this is this notion of framing and reframing, and how the value systems as you frame change. If you decide to get rid of gears in a mechatronic system, everything to do with gears disappears and something else comes in. So if you're going to shift from hardware to software, which is a big shift today in designing, all the value systems associated with hardware are just not applicable. Who cares about weight? Who cares about friction, about system maintenance, and so on? It's situated. That is, what's happening around you changes everything. Night and day are not the same. And designers learn while they're designing. So it's a continuous learning activity. And finally, even the criteria used to assess a design changes depending on what you're designing, what it is you produce. And then the design has this characteristic, which many other systems do. It's non-monotonic. Just because you took a decision, the decision doesn't stay taken. You upset it, you change it, you untake it. A lot of issues there. So finally, what is the future of AI in design? Will design be automated? No. Some aspects will. In fact, many aspects will. We can see that deep learning gives us access, if we have the data, to replace the data with an accessible representation of a set that is much, much, much larger than the data source. But there's a lot of other techniques that assist in automation. Automation is removing humans. Will designing be augmented? Not automated, augmented, added to? And the answer is clearly yes. In all other human endeavor, we see augmentation. And we've seen it. I've tried to give you some examples of that. Will co-creation become possible? Co-creation is where a tool is no longer subservient to its user, but moves up and becomes semi-autonomous and not just reactive, but which is, our tools today are reactive. You do something, they respond. You respond, they respond. But they don't respond if you don't do anything. Co-creation implies that the co-creator initiates. So AIs will become low-level partners. And there are likely to be new areas for AI in design. And the biggest one's likely to be things like multimodal learning. Instead of just learning about the thing you're doing, maybe you'll learn about lots of other things, like about the designer. What's the effect of that? There's lots of studies that show things which we take to be objective decisions are actually a function of the state of the human taking them. If you ever go to court, it's really important that the judge not take a decision about your case while she has lowered sugar in her blood, because statistically you are going to be found guilty. Same applies with designing, presumably. And then, one of the interesting steps is integrating brain sensing with AIs of humans. And I don't know if you've seen this. This is a $998 brain sensing device from Emotive. And what you see is real time. Its person is thinking Zoom, and an AI is learning the brain pattern for Zoom. It's now learned it. It connects it to the CAD command Zoom, and the person is now thinking Zoom. That's it. This is real time. So we can transfer commands just like that. So we can do a lot of brain sensing. But there's pitfalls in all of this. The most common one is this one: unintended consequences, right? And we did a study of using a learned generative system to produce designs. And then we learned from the designs it produced a refinement of that generative system, and then learned from the design it produced. And after a while, it ended up producing one design, but very quickly. That's a clear pitfall. And then always, and never at the end, what are the ethics of doing this? We're dealing with people and their lives. The future of AI and design, I think, is fantastic in both senses of the word. And it's going to be fun. And I'm required to put this up here but I would anyway. The ARC, DARPA, NASA, and NSF are all surprisingly generous to me and have given extraordinary amounts of money at some of the results you see here. And with that, I'll stop.
Thank you very much. That was great. It was very, very interesting, cool, and a fantastic journey through your work and the history of AI in the design context. Now I just need to organize a bit here.
Here. I have the questions from the audience up. I think maybe we can ask a few here. I think I'll actually start with the last one from Gabriella. 30 years after writing 10 problems in AI for AI in design, which do you think will persist and which are closer to being solved by current tools?
Okay, that's a really nice question. I think all of them persist. That's the beauty of human activity, that you very rarely get rid of problems. You work them into your world. I think the problem that we are focusing on today is that we actually can do a lot more than we ever thought we could. And it's a question of making that useful. But the problems of representation and reasoning, they're all there. As I said, I think the one problem which we were unaware of 30 years ago, and we, much to our shame, I believe, is the problem of the ethics. That to me is the biggest problem, actually, that we really tag on at the end ethics instead of making it part of the way in which we think about everything.
Another question from the audience from Chen was, creative design or non-routine design requires divergent thinking. Do you have any thoughts on how AI could assist human designers regarding this aspect of the work? So thinking about divergent thinking in design.
Thank you for the question, because this is a fundamental question. Divergent thinking is a psychological idea, found its way into cognitive science and then into AI. And it's situated. What do I mean by situated? It depends where you're looking from as to what is divergent. If you have an extraordinarily large design space, you could end up in places that no one has ever ended up in before and would therefore look like divergent. So that's one boundary condition, and one that is a common condition, a common claim by people in deep learning doing generative systems. But we've seen that with tools like Analogy, you can end up in places that didn't exist before. And that's what we tend to think of as divergent thinking. But you can build systems that move you to such things. John Kagan, in his PhD 30 odd years ago, built a system that used one rule, which was take a variable, divide it into two. And with that, he was able to invent the wheel. Literally, I mean. So, yes, but I don't think divergent thinking is much. It's an element in the notion of creativity.
One question actually from Randall is also associated with this idea of analogy in your discussion of analogy. And you mentioned that Dendra Genter's work and structure mapping engines seem to produce boring results. Randall asked, do you have any thoughts on Douglas Hofstadter's work on analogy?
Yes. Now, his work on SLIP was more interesting because it used a sort of a different approach. I think they all miss something. I mean, they're fantastic. I mean, the structure mapping engine is a foundational idea. And Hofstadter's work is always so illuminating. But they miss something which I think humans do, and therefore we don't learn enough. I don't think humans work the way any of these work, although Hofstadter would certainly disagree with me. And let me give you a simple entree into this. When we build computer systems, we build representations and we build processes. And the process has to operate on a representation. You know, if we're expecting numbers and we only see letters, it fails. If we're expecting lines and it sees pixels, it doesn't know what to do. I don't think humans work like that all the time. I think humans construct the representation to allow them to do what they want to do. And Jared Kalinske and I built the beginnings of an analogy system where you didn't need to have a representation of the thing that looked like what you were looking for. It went out and said, can you represent yourself the way I want you to? And if you can, then I'll look at you. So this is an inversion. So I think there's a lot more. I mean, AI is not finished. Deep learning is not the end of AI. Deep learning is a step. And because it's so powerful, we've lost track of lots of other parallel things that are happening that are also very interesting. And then, you know, as I say, deep learning is taking over everything. But those of us who remember, sorry, something's appeared on my screen. remember, expert systems were also the solution to the universe's question. Yeah.
Another question here from Aiden relates actually to how you were talking about one of the fundamental flaws of deep learning methods are that they really can only represent within the bounds of the training set. And I didn't actually ask, how do you think about the role of increasing usages of BIM models in architecture and construction and building, and how that might change the development of applications with AI? I guess maybe one thing that I'm thinking of here is that we now have the ability to capture so much more data about what we're constructing and what we're building. How might that be used or misused potentially in AI-based design applications in the future?
Okay. Firstly, I think BIM models are fantastic, particularly if they go the richer ones. I mean, the ideas go back, you know, if you look at, there was a system in the 1970s called the building design system that did everything BIM did, but BIM hadn't been invented yet. Very few ideas are really new. BIM has the failing that every system must have. And that is, it doesn't look at anything outside what it does. Right? If you don't capture the fact that stiletto heels produce enormous pressure on floors, it doesn't exist for you, right? That actually was a problem in a library I was involved in, where we had this beautiful flooring system that dampened sound, but you know, no one took account of the fact that people wore stiletto heels and punctured it. So yes, we are generating the data needed for deep learning. Not a new idea. I mean, I did a consulting project in the late 60s for, I can't say whom, but a big hospital owner that owned lots and lots of hospitals, where the goal was to predict what size, whether it needed a surgical ward based on the demographic information and what size things should be roughly, based on 124 hospitals that they owned. So that idea is not new. What's new is the level of detail we can generate is new. What isn't there is if someone comes up with something that replaces, say, pipes. Now the BIM model doesn't know what to do with that. And we've had this, we've had central air conditioning where you pump air all over the place. The next thing we know, we have multi-zone systems, multi-split systems where you don't move air around. So that means you have to constantly expand, is the lesson from that.
Actually, just to add on to that, I'm curious, the fact that we can capture so much data and we can really utilize that in a lot of systems, but it's still the things like you're saying that we either don't capture or that we are not thinking about moving beyond. I guess in this way, how do you see designers playing a role in maybe continually sort of adding to the systems of we should capture, we should model how people walk on floors and the nature of shoes, right? You have one issue and now you can model that. Someone could go out and start taking a bunch of data, running a bunch of simulations. Could be an entire company that does literally floor analysis. But I'm curious as to where do you see the designer or the design team's role in sort of adding to that data capture and thinking about what needs to be captured?
Okay, I think, and this is a truly serious issue. What's missing, and we've known it's been missing in the we know why it's missing, is what happens in a building with a design, with an artifact, with a machine, with a device after or during its use. Because we've been taught that designing finishes at a certain point. And then we go home. And the reason is that no one pays the designer to look at it afterwards, right? But we now have both physical and social tools to measure way beyond that, to measure the use of our designs. And we should be taking account of that. Not just measuring the design, but measuring its use. So that's because, and let me just give you a little story. A colleague of mine, Tony Radford, and his students wanted to produce a shape grammar for a famous architect, an Australian architect. And we got access to his last 6 houses, and they produced this grammar. And he happened to be a neighbor of mine. And I said, look, can you give us access to a design you're working on right now? And we'll produce a design based on this generative system. And we showed it to him, and he looked at it and says, oh yeah, that looks okay. But I wouldn't do that. And so we went back and said, well, you did it in this house and that house. He says, oh yeah. When I did it on that house, it really worked well. On this house, though, the vista and so on just wasn't good. And when I did it on this house, I said to myself, I will never do that again. Right? That's not in the design. Right? So when we capture the past, we're only capturing, and that's what we do in learning, we're only capturing part of the past. And right? So what's missing is the behavioral evaluation of the designs. And when you look at all the stuff that's being learned through deep learning, it tends to be about form, not function. It tends to be about the thing, not whether it worked well or not. So in my terminology, we capture the structure, very little behavior, and no function. And that, I think, tells us where designers should contribute to make this fantastic tool truly more useful. You've got to capture at least behavior. Not capturing behavior, you're like an animal who knows nothing about the world except don't bump into things. All right, you just know its form. And therefore there's no trajectory. The other thing that's missing in what we do, and it's not missing, it's just we don't do it, and that's the temporal aspect of learning. What we designed 5 years ago is not necessarily relevant today.
I want to bring up a question here from Lorenzo, which is, how do you think that some of these new technologies, and maybe some of the thinking that you're discussing here, should be applied to, Lorenzo asked about architectural education. I'll actually expand that to design education in general. And maybe what are some of the new areas of expertise that may be required, and what kinds of courses should we be thinking about providing to students?
Well, I think there's a number of things, but let me start off with what I think is a fundamental one. I think all educated people should learn 2 types of thinking. One is design thinking, and the other is computational thinking. Computational thinking is not about computer science. It's a way of thinking about the world and how to deal with it. And design thinking and computational thinking are opposite ends of a conceptual view of the world, because what designers do is try and make things specific to the task by including as much as, and include as much as they can. They look at culture, history, whatever. Computational thinking is to abstract things as much as possible and make what you produce as general as possible. You know, there's only 2 or 3 navigation systems that are used on phones in the world. And it doesn't matter where you use it. Munich, you can find it. Tel Aviv, you can find that. You know, Manhattan, you can find what you're looking for. Same algorithm. Design doesn't look like that. Right? Design looks totally different. So I think there's 2 kinds of thinking we all need to be schooled in. Now, precisely what other particular technical skills one needs, I don't think every designer should look the same. I think that you need a range of designers. And so I don't think designers should learn statistics unless they're in a world that statistics is interesting. I mean, if you want to be a designer of buildings in New York, you better have a very, very good understanding of economics, because that's what drives New York buildings. If you want to design a church on a mountaintop in Switzerland, economics isn't going to be interesting. So I don't think there is one answer for that question. I think one should learn that there's a lot of stuff around so that you know about it, but not that you are skilled in it. The thing you should be skilled in is designing.
Maybe to add on to this too, I'm curious about your thoughts. So I think sometimes when we talk about designing, we think about a designer, like an individual, but today, and many things are done by design teams. How are you thinking about sort of future design teams in both the composition of people, but people in relation to maybe AI-based design agents, and how they're sort of all interacting together?
Well, I think you've hit on another one of these fundamental questions, which is how teams work and how they should be put together. We're about to publish a paper on how teams naturally, independently of how they're composed, naturally behave in, let's say, in sub-teams. That it turns out there are people who like to make comments on everything, and there are people who specialize. So we'll call them generalists, sub-teams, and specialist sub-teams. And when you match that with the structure that's laid out in the organizational chart, you discover it's not the same, right? The person brought in for this specialty, and therefore you wouldn't expect to contribute to all this other stuff, does. So it turns out the behavior of people, is, as we know, is not always predictable. So now let's go back a little bit. When you study teams, you discover, and teams have been studied by management much more than in the design world, you discover something which all team managers know, which is when people work together, they get more efficient at producing results. But there's a cost, and the cost is a reduction in the diversity of ideas. So now you have to decide what's the purpose of the team at that level. If you want to produce something quickly, produce a team of people who worked together before. If you want to get better ideas, bring in people who haven't worked together before, or at least bring in one or two people who haven't worked with them before, preferably people who like to make a lot of noise, because you have to be heard as well. So one thing we ask students to do is to work together in teams, but we don't give them any guidance. Why? Why don't we? We give them guidance on everything else. Why don't we also, as part of their education, educate them in terms of team behavior? So that's a lack in our formal education of designers. We know a lot about team behavior. I mean, if you look at the great design teams, and I'm talking about, the people at Apple, the people at Xerox PARC, the people at Boeing, Lockheed, who produced the first commercial jets and all that sort of stuff. You discover one thing they have in common, and then very few other things. The first is, and remember, these are all in commercial organizations. The first is that they're insulated from the rest of the organization. That seems to be the most profound thing you can do. Stop the rest of the organization from interfering. The second is to have a charismatic leader who needn't be the best in whatever's going on, but charismatic in the sense that you'll follow him or her. And the third is there needs to be a vision. But none of those are themselves skills that you teach, which is a little unfortunate. But also, I think, good, because if you could teach it, then it would diminish it, and probably you'd put it into an AI and so on.
Building a little bit on that, on things that maybe we're not teaching, or maybe they're not as explicit. And also I want to reference Gabrielle's question here, which is, what do you think the current trend of design in uncritically applying deep learning techniques, especially in generative models? You had mentioned a lot about ethics and ethics in design. And I think today, one of the things that we see is there's a lot of excitement around, okay, let's apply this tool. It's very exciting, but as you mentioned, there's always going to be unintended consequences. How do you think about engaging designers in that critical thought about looking forward to potential unintended consequences? And how do you potentially bring in some of the work being done within the AI field in this space to a design conversation?
Well, of course, the thing about unintended consequences is you don't know them beforehand. But it doesn't mean you shouldn't be on the lookout for it and prepare yourself. And you could, in a thought experiment, divide unintended consequences into two. But it's never that simple. One is that it's beneficial in design terms. Right? And in that, or beneficial to, let's wave our hands and say, society. And then there are those that are not beneficial in design terms and not beneficial to society. Right? So, but at the same time, one needs to be aware that the goal of keeping the world static is a fundamentally flawed idea. And what do I mean by that? Design changes the world and therefore disrupts things. I don't know if you're familiar with a term that Joseph Schumpeter, who is an economist, coined to attempt to conceptualize what makes American capitalism so powerful. He coined this term called creative destruction, which is a profound idea. And what is creative destruction? It's when you produce ideas that destroy the value systems that were used previously. And let me give you an example of that. When you have to be my age roughly to know, but you might have heard that the Sony Walkman. The Sony Walkman was a little device you slipped in your pocket and you had earbuds. But it was designed to replace a device for listening to music in public. And that device was a boombox. It weighed, 10 kilos and was, 20 pounds, it was a meat, this big, sat on your shoulder. And by, we can go through the design processes, how they went from this huge box to this little box. But the effect of it was it put all the manufacturers of those boom boxes out of business. Almost overnight, in 18 months, there was an 80% reduction in demand for those things. Well, that's an unintended consequence that is clearly bad for those businesses. But it wouldn't have made sense to prop them up because the world changes. And as designers, we make it change. That's our business. Our business is to change the world. So when we talk about ethics, we don't mean, no one should lose their job. What we mean is we create a world where it's possible for people to transition out of a job that's going to be destroyed. That's where the ethics comes in. What is a mixture of social responsibility and how we change society to take that responsibility? Yes, we can keep coal miners in business a little longer, but the long-term prognosis for coal mining is in the next 50 years, certainly in 100, it'll disappear. It'll go to zero by design. So yeah, I think ethics should always be taught as part of things, and designing perhaps even more than most, because just to reiterate, our business is to make the world change.
So I think we have time for one more question, and there's a number of students who are here in the audience, and I've seen a couple questions from students. I want to thank all the students for joining today. Maybe as a final closing thought for everybody, for those who are just starting in their career, whether it be in undergraduate or graduate school, or they've just recently graduated, what advice might you give to them as they start to think about the changing nature and the changing role of the designer as we start to create more AI-based design assistants?
One should never give advice. So here's a little bit of advice. The best thing to do in life is to follow your passion. After that, everything fits in. I mean, sometimes it doesn't fit in where you want. If you want to be a professor, you need a PhD. And if you say, I'm not going to get one, well, it's just, you have to change society, which is going to be hard for you. But, everyone lives their own life in the end. It's unique. The situations you encounter and your responses to them. Just do the things you believe in. Now, it doesn't mean, if you believe in murdering people, well, that's probably not a good thing to follow if you're a psychopath. But, you know, you have an area you're in, you're passionate about it, equip yourself. Now, if that means learn a lot of AI, well, yeah. No. I think the notion that, you know, it's funny for designers to think that when they finish school, they're complete and all they need is experience. Since their business is to change the world, they have to change too. So the way that what you would expect to get out of a good education is your passion is fed. You don't go in passionate and leave disillusioned. That's the opposite of education. It equips you to do things that you never thought you would have to do as you go on. I mean, I'm always taken by, I had a daughter who did engineering at MIT, and one of the phrases she said regularly after graduation was when, you know, she was looking around or whatever, and she would say, look, of course I can do that. I'm an MIT graduate. So what did she learn from that? I mean, it's hubris and all sorts of other things, but what they learned was that they have this capability to do things. But, oh, I never learned that, so I can't do that. And that's very powerful. So I think education is about learning to educate yourself. And along the way, you develop all these skills so that you're socially useful when you graduate. So there is no answer. It's what is known as a wicked problem, right? Whatever you do changes what you've done, and now you have to do something else.
Fantastic. John, thank you so much for the inspiring talk. I don't know if you have been following, but a number of people have said thank you and inspiring talk within the chat. The fact that you kind of took a really nice historical perspective, looking at where we've been, where we sort of are today, and then where we can go to the future, I think was quite impressive. And I think it really puts a lot of what we're probably seeing today in a much broader perspective, which I think is quite useful. And then also thank you so much for being so open for quite a long question and answer session. To those in the audience, thank you for attending today and for asking very thought-provoking questions. We hope that you enjoyed the talk, and we wish you the best in the rest of your endeavors.
Hear, hear. Okay. Much of what I've talked about, I've written, not much, everything I've talked about, except the extemporaneous stuff I've written. And if you look, I write voluminously with lots and lots of people, and most of it's downloadable or accessible.
I actually just shared your Google Scholar link, which should have links to all of the papers and things. So yeah, even including the newest work on the neurocognitive feedback that is up there right at the top if you sort by year. So wonderful. Well, thank you all for attending, and have a great rest of your day.
And thank you for the opportunity.
There is a question on the recording. Yes, the recording can be made available. So the session was recorded, so we can make this available to folks. Oh, and there was John, I'm sorry, there was a question earlier, which was if you would be willing to share your slides. That's up to you, but just
Yes, I'm happy to share my slides as a PDF, so you missed the videos.
Sure. I think that would be
not
fine.
that I'm against you having the videos, just that they don't play everywhere.
Yeah, I completely understand that. Anytime I try to share something and the videos never work. So a PDF. So then we should be able to share both the recording and the slides from the talk. So yeah, if anyone missed any part of it, you should be able to go back to those.
Yep.
Great. All right. Well, thanks everybody. Have a great rest of your day.